Okay, for a general equation of A plus B plus C, I'm going to show you right now how to determine the exponents on the rate law. So the first thing we need to do if we're doing a question, and keep in mind that you're going to be given a data table, and I'll go back and show you this. I know I showed it to you once already. I'm going to be giving you a data table like this, and we need to be able to determine what the effect of changing these concentrations are on the rate. So we need to do a little bit of mathematical manipulation so we can see how many times greater the rate is when we change the concentration, all right? So that's the whole purpose of this particular exercise. Because once we have the rate law from yesterday's lesson, you should know how to then determine the changes and also determine what the K is, and then ultimately use the rate law to determine the rate. So the first thing that we do, whether I got a general situation here or an actual one, is to write down what that rate law would look like, putting in the variables that we're looking for. So in this case, rate is equal to K, and that is going to be equal to the concentration of A to the exponent X times the concentration of Y to the exponent, whoops, look at there, I screwed up already, B to the exponent Y, all right? So essentially what we want to do is we want to find out what X and Y is. Now this is an exercise in our variables when it comes to experiments. With an experiment like this, we're truly going to have a situation where we have to keep B constant so that we can look at the effect of A on the rate. And that's because we need a controlled variable when we change our independent variable, A, to see how it changes the rate or the dependent variable. So we always must keep one thing constant. We call that the controlled variable, all right? So when we want to determine the exponent on A, we need to have constant B. So for the concentration of B constant, we can then analyze what happens to A. Now we've already gone through the preliminary part of this. We're going to pick some data where B is constant, and if that's true, then we can make the statement that rate 2 is equal to K. This is going to be times A2 to the exponent X times B also to the exponent Y. But I'm leaving B constant, so I don't need to worry about whether it's the final concentration or the initial. Now yesterday we divided off R1, the rate law, at the initial concentration. That's going to be equal to K, again, times the concentration initially to the exponent X times the concentration of B to the exponent Y. Now, due to the fact that we've chose an experiment where B is constant, these B terms will cancel out. And because the constant is constant, that's funny, these constants will cancel out. And that's going to leave us with the same equation we used yesterday, R2 over R1 is equal to the concentration of A 2 squared, to the X, we don't know what that value is, A 1 to the X. And what we want to determine is that exponent X. And so that's where we left off yesterday. And so here's how we're going to figure out what the X is. I'm going to head over to this side here. One last step before we use the logarithm, R2 over R1. And because these are both to the same exponent X on the other side here, I can pull that exponent X and I can have A, concentration of A final, concentration of A initial, and that's all to the exponent X. So I can take that exponent out of the brackets. Now here's where the log part comes in. What we want to do mathematically now is take the log of both sides. All right? If we do one thing to one side, we got to do the same to the other side. And all we're going to do is take the logarithm of both. So the log of R2 over R1 is equal to the log of a concentration of A final 2 over A initial 1, all to the exponent x. And here's where the logarithm comes in handy. The neat thing about the logarithm is that when we have a log of something that has an exponent, that exponent can come out in front of the logarithm. All right? Don't ask me why. Ask a math teacher. I really have no idea. It's just a neat thing that you can do when you take the log of a number. So what that means is you end up with the log of R2 over R1 is equal to x times the log of the concentration of A final over the concentration of A initial. Okay, we're almost done here. The last step is to isolate for x. So if we divide off this log of the concentrations and put it on the bottom, then we finally have what that x value is. So the log of R2 over R1 over the log of the concentration of A final over A initial is equal to x. And right there is our final equation, the final version that we're going to use to calculate what that exponent is. All right? Now we will do the exact same procedure when dealing with B, except we need to have a constant and we will follow the same logic. I will not expect you to derive this equation. Save that for Mr. Petrus's physics class. All I want you to do is be able to use the equation. But it is very often useful to know exactly where that particular equation is coming from.